in the Schrodinger equation, there are 4 quantum numbers that you need to plug in. So if you plug in a value, so the Schrodinger equation has a place to plug in a value for n, l, ml, and ms, which we'll talk about. When you plug in values for those 4 quantum numbers, you plug them into the formula, you get a wave, an equation for the wave, and when you square that, that's where you get these 3-dimensional regions. Okay, so we have to talk about these quantum numbers because they describe the different shapes and different possible locations for the electrons, and later we'll match up the quantum numbers with the periodic table so we can see how the different elements have their electrons in areas with different quantum numbers. So let's talk about these quantum numbers one at a time. So the principal quantum number we've already talked about, that's n. Right? That basically just tells you which principal energy level or which energy level the electrons are in, and these are also the same values for n that we talked about in the Bohr model for the hydrogen. Right? So this is the most straightforward one. If you're in the nucleus, there is no value for n, right? Because electrons are not in the nucleus, right? So these quantum numbers are describing the areas that the electrons are in. So the electron could be in n equals 1, or it could be next out, n equals 2, right? As we go further and further away, we're increasing the value for n. So n relates to the most general location for the electron. It basically just tells you roughly how far away the electron is from the nucleus, right? Because the lower the value for n, the closer the energy level is to the nucleus that that electron is in. Right? So the next value is L. So I like to make an analogy here because these are pretty abstract. So my analogy is the LCCC campus, and I'll relate that to an atom. Right? So in the LCCC campus, let's say I wanted to locate a specific student. So I know the student's on campus, just like I know an electron is somewhere in my atom. Right? The campus has buildings. Within the buildings there are rooms. Right? Within the buildings there are like a first floor and a second floor. Within each floor there are rooms. So there are certain levels of information I can get about the student's location. Just like in the atom, there are certain levels of information I can get about where the electron is located. So we just talked about n. N gives me the least amount of information, right? So if I know the student's on campus, but I don't know where they are, the first thing I would want to know is what building they're in, right? So the building is like knowing the value for n. That really just tells you the energy level. It doesn't tell you really where the electron is. Just like on campus, there are multiple rooms and floors within the buildings, there are multiple areas within these energy levels, smaller areas that make up these energy levels that we want to know where the electron is in those levels. Okay? So within a building, there are floors, first floor, second floor. Within a floor, there are rooms. And so that's the level, that's the level we need to go to. And what we just said was, if we can tell what orbital the electron is in, that gives us a three-dimensional shape for the area that that electron is in. But we never know exactly where the electron is. The electron behaves as a wave, so it's all over that area at once. So that's the orbital. So that's as close as we can get. If you're looking for an electron in an atom, that's like looking for a student in a room where you know they're in the room, but they're like the X-Men character Quicksilver or something, and they're moving so fast around the room, they behave as if they're everywhere in that room at once. So you have maybe a probability that they're, the density for that student in the room is closer maybe to the center of the room than the edge, but you don't know where they are in that room. Right? So that's how electrons behave in an orbital. We can tell what orbit they're in if we know the quantum number that describes that electron, but we don't know where it is in there. And so the intermediate level, like a floor is in a building and there are rooms within the floor, the intermediate level of description for the electron is called a subshell. So if I know the energy level for the electron, that's some information. But if I want more detail, I need to know what subshell within the energy level the electron is in. If I know what subshell the electron is in, then I could also know potentially what orbital within that subshell. Right? So these are areas within larger areas that we're talking about. So the L quantum number tells you this is associated with the subshell. And different subshells have different shapes. Right? Just like certain buildings, based on the shape of the building, would potentially create round rooms versus square rooms or something like that. My analogy is starting to break down. But there are only really 4 that we're going to be concerned with. 4 different possible subshells. And they, based on the value for L, so L could be equal to 0, 1, 2, or 3. The subshells that relate to those values are S, P, D, and F. So we'll talk about the shapes of these here in a second. But the value for L also, though, does depend on the value for N. So let's talk about this. So when N is 1, right, that's the one that's closest to the nucleus. So if my nucleus is here, the N equals 1 is very close. When N equals 1, if I'm very close to the nucleus, am I going to be able to fit a lot of electrons or only a few? You might think I could fit a lot in there because they're all attracted to the positive charge of the nucleus. But remember, the negative charges of the electrons also repel one another, so I can only fit 2. I can only fit 2 electrons in the whole entire first energy level in any atom. And so within that energy level, since I can only fit 2 electrons, there's only one subshell. So there's one subshell. I left out a U there. Imagine I put a U between that S and that B. In one subshell, that means there is only one value for L, and that is 0. And when L equals 0, I'm talking about an S subshell. That's the shape. And an S is spherical. So anytime N is 1, L must be 0. Because in that area right next to the nucleus, there is only space for one subshell, and it is a spherical shape. When I'm in the next energy level, N equals 2, now I'm talking about, so let's get rid of this one, so we can just look at N equals 2. Now I'm talking about an area that's a little bit further away from the nucleus. Now I've got a little bit more space, so I can fit a lot more electrons. So now in N equals 2, instead of there only being space for one subshell, there's space for 2 subshells. So that leads to a trend which we would see if we went into more depth here, but I can just tell you what it is. The number of subshells in an energy level is equal to the value for N that describes that level. Right, so if we're talking about energy level N equals 1, there's one subshell. In N equals 2, there's 2 subshells. In N equals 3, there's 3 subshells. In N equals 4, there's 4 subshells, and so on and so forth. So if in N equals 2, since there are 2 subshells, each subshell needs its own quantum number. So when N equals 2, L can be equal to 0, or it can be equal to 1. And what we just saw is when L equals 0, that is an S subshell. I did it again. That's weird. S subshell, which is also spherical. All S subshells are spherical. But when L equals 1, that has a different shape. That is a P subshell. Questions so far? So we'll see the shape of a P here in a minute. So if we look at n equals 2, well, I'll just show you here. So in n equals 2, there's a spherical one, and there's also actually 3 P subshells, and each of those lies on a different axis. So there's a P subshell on the x-axis, and this is what it looks like. So it's got 2 lobes. That's Px. There's one on the y-axis, Py, and there's one on the z-axis that I can't draw because I'm limited to 2 dimensions here. That would be coming out at you. So imagine that pointing out of the screen at you and also pointing away from the screen behind. Just to point out, in a P subshell, so the 2 areas I just highlighted in yellow, those are both areas of the same subshell. They're not 2 different subshells. Okay? So, in this case, if we're talking about n equals 2, this building has 2 stories, 2 floors. On the first floor, I've got an S subshell. On the second floor, I've got a P subshell. Within an S subshell, there's only one room. An S subshell is always spherical, and it only has enough space for one orbital or one room. I can't fit more than 2 electrons ever in any S subshell. A P subshell, though, has 3 rooms. 3 orbitals fit in a P subshell. And there's always one on the x-axis, one on the y-axis, and one on the z-axis. So when I get to n equals 3, now I have more possibilities. So in n equals 3, now I have 3 floors. So this is a building with 3 stories. There's an S subshell, there's a P, and there's a D. So again, the S subshell is spherical, and it has one room, one orbital. The number of orbitals in an S subshell is always 1. How many orbitals are in a P subshell? 3. So if we went with that trend and continued it, how many subshells would you expect would be in a D? I'm sorry, how many orbitals would you expect to be in a D subshell? 5. And those are going to be more challenging for me to draw, so I will show you those shapes here in a minute. If we went to n equals 4, now we have a 4-story building, and there are 4 subshells within that energy level. There's the S, there's the P, there's the D, and there's the F. Again, S is always small, so even in the 4S, it's still only one orbital. In the 4p, still 3 orbitals. In the 4d, there are 5 orbitals. In the 4f, there are 7. Right? So the trend continues. So this is just a bunch of numbers, and we need to have a visual to kind of relate these numbers to. So let's keep moving forward, and we'll see. So this just kind of shows you what we just saw, right? So if I'm talking about an area that's further away from the nucleus, I can fit a lot more electrons. How many total electrons can I fit in n equals 4? How would I answer that? Well, I would recognize that each of these boxes represents an orbital. So every orbital has a max of 2 electrons. So in any S orbital or S subshell, I can only fit 2 electrons. In any P, since that's 3 orbitals, that's a total of 6 electrons. In any D subshell, that has 5 orbitals, I can fit up to 10 electrons. In any F subshell, that's 7 orbitals, that's up to 14 electrons. So I would just add that together, and I would get 32 electrons total in the 4th energy level. What's the minimum number of electrons? 0. We already said I can knock all the electrons out if I have enough energy. The minimum is always 0. All right, let's come back to this. I think it'll be helpful if we have. We're not gonna see those shapes a little bit till next time. Never mind. We'll have to do that next time. There's only so much time. So let's just answer these examples. So there are also some rules which I kind of glossed over, but we'll show these in the examples. For predicting quantum numbers, so there's the n. N can be anything starting from 1 to infinity. It cannot be 0, and it cannot be a fraction. It has to be a whole number starting with 1. So n cannot be 0, and n cannot be any decimal or fraction. The possible values for L depend on what n is equal to. L equals n minus 1. I'm sorry. L equals L can always possibly be 0. There's never a situation where L couldn't possibly be equal to 0. So L is going to be 0, and then other whole numbers up to n minus 1. So that means that L can never be equal to n. And so remember, L tells me whether I'm dealing with an S, P, D, or F subshell. If I know the principal energy level, that at least tells me what limitations I have on the possible subshells that are there. ML is the quantum number that tells me which orbital within the subshell my electron is in. And so that is equal to this here. ML is also a whole number integer, but it could be negative. Right? So I didn't say that here. I probably should. N cannot be negative. And L cannot be equal to N. L cannot be negative. Sorry about that. ML ranges from negative L up to 0 and then up to positive L. And we'll talk about MS here in a second, but MS only has 2 possible values, negative 1/2 or positive 1/2. So that's the simplest one. All right, so let's look at this question. When n equals 3, what are the possible values for ML? Let's also assume L is equal to 1. Yeah, so actually this is unnecessary information here, n equals 3. We don't even need to know that. As soon as I know that L is equal to 1, the possible values for ML are based on this, negative 1, 0, and 1. The fact that when L equals 1, ML is negative 1, 0, or 1, that's not just possible number values. That gives me information about what we're talking about. When L is equal to 1, I'm talking about a p subshell. And how many orbitals are in a p subshell? 3. That's why there are 3 different possible values for ML. Each represents one of the 3 total orbitals that are in that p subshell. And when I know there are 3 orbitals, how many total electrons could there be? Anywhere from 0 to 6 electrons can fit in that subshell. 2 in each orbital is the maximum. Okay, questions about that? All right, let's look at 3.77. Describe the characteristics of an s orbital. It's spherical. A p orbital has more of a lobe shape, and a d orbital has more of a four-leaf clover shape. I'll just show you those and we can talk about it more next time, just to quickly show you the shapes. These are the 5 shapes for the d orbitals. So 4 of them have a four-leaf clover, and they are all on different axes, three-dimensionally. The 5th one is a weird kind of double lobe thing with a donut around it. So again, those shapes come from the Schrodinger equation. So there are 5 different d orbitals, and those are their shapes. So just to give you a preview for that. But the second part of this question is really what I wanted to look at. It lists a bunch of orbitals and says which of these orbitals do not exist. So let's just talk about these real quick. The first one is a 1p. Is it possible for that orbital to exist? No. When n equals 1, the possible values for L are 0. That's it. L must be equal to 0. And when L equals 0, that's an S subshell. So in the first energy level, that's what this notation is showing. The 1 here means we're talking about the first energy level. The only thing that's there is a 1s. There is no 1p or 1d or anything like that. 2s, that's fine. You can have that. 2d, no, that does not exist. So if we look at a 2d, if we're looking at a 2, we're talking about n equals 2. And in a d subshell, if we did have that, L would be equal to 2. So we just said n and L cannot be equal. The maximum value for L is whatever n is minus 1. So in the second energy level, there is no d. In the second energy level, there's an S and there's a p. That's it. 3p, that exists. 3d, that exists. 3f does not exist. And 4g. Let's see, 4g, that would be n equals 4. So when n equals 4, the possible values for L are 0, 1, 2, and 3. So that's an S, P, D, and F. So there is no G in the 4th energy level. There's a G in the 5th energy level. But none of the electrons on the periodic table have electrons in a G anyway, so we're not going to really be talking about that. But in the 4th energy level, you can have S, P, D, or F. That's it. Questions about that? 3.78, why is the boundary surface diagram useful in representing an atomic orbital? So what we're talking about there is the difference between this versus this. So this is very nice. It shows the probability for the electron's location. It also shows, the more darker the area, the more probability the electron's located in. This boundary surface area puts a boundary on that. So the problem with that is it's not really correct. If we looked at the actual probability for where the electrons are in this 2p orbital, we would see that the area where it's darkest, over here, that's where the highest probability of finding the electron is. But the probability never goes to 0 except when I'm in the node. As I move out of this orbital, the probability drops quick and it approaches 0, but it never actually completely goes away. So the problem with the boundary, putting a boundary on that, is there is no actual boundary there. The probability of finding the electron, there's some probability the electron's actually out here at this distance. It's a very low probability, and the electron's average energy is not going to be affected by that probability, since it's not much of a probability at all, but still some probability there. So since there are no boundaries, except the electron cannot be on the node, these boundaries are kind of fake. But they are useful because within this boundary is the 90%. The 90% of where the electron's located is within that boundary. And since the electron's everywhere at once, only the areas of highest probability for where the electron's located are really going to be impacting the energy of the electron, which is what we're most interested in. The average location is going to be really determined by how much area is taken up by that within the 90% boundary. So that's why that boundary is used, because it helps us to understand where the electron's most probable location is, and that tells us about the energy of the electron. Any questions about that? Okay, so the spin part, most students don't have any trouble with this. The spin quantum number is the fourth one. That's either plus 1/2 or minus 1/2. That means the electron has two possible ways it can spin. It can spin up or it can spin down. And when you have a charged particle spinning in some direction, that creates a magnetic field. So the spin of the electrons is what's responsible for the magnetic properties of substances, or for magnetism. If you take a charged particle and spin it, you'll create a magnetic field in a direction that's 90 degrees to the spinning direction. And so since some electrons spin one way and other electrons spin the opposite way, those magnetic poles actually cancel one another if we have equal numbers of electrons spinning in opposite direction. And so you can do an experiment where you can show with a magnet the electrons separating based on their different spins. So you can see that matter that has an even number of electrons. So when you have an even total number of electrons, not always, but sometimes half of the electrons spin one way with a plus 1/2 quantum number, and the others spin with a negative 1/2 quantum number. So you can actually separate the different electrons with the different quantum numbers and show that they have different magnetic spins. So that's just the experiment that allowed scientists to make that determination. So this is notation. We'll talk more about this next time. So let's just pick up here next time.